Yeah, except that chain, I think everything is working fine. And that chain is super low power. I checked, I compared the amplitude with the other feed, so that's probably huge. So I would say it's not. 就是这个东西你在苏大做就不会就没有这个 phase， 你知道吗？就第一个 phase 就是一块 PCB， 或者几块 PCB。
做什么？
啊，对，买不起，所以才 PCB， 才打板子。苏大能比较学上。
做 PCB 还要花时间。
对啊，花时间和花钱，老师当然愿意花时间了，对吧？你跟老师说，老师啊，我今天要买一个元件，老师说多少钱啊？哦，3000刀。然后说你走，这实验室不欢迎你，你走。你说老师啊，我最近画了一块板子，我想试一试。老师说那打块板子多少钱啊？15块100块，打，马上打。
但是你去画那个高速板子时间，
对啊。所以才值钱啊！这种人在中国，你跟老师说，老师我能画15G 的板子，我操，你就是大爷，你想干嘛干嘛，没随便你怎么干什么东西。I think we just stand over here and wait until 5:30 and shit.
So how does this lens work?
So it's just using for the spatial Fourier transform. So basically, it's used to generate analog beams. So we got the.
So how is the lens designed?
How is the lens designed? I'm not really sure about that. I think
It's just a optical concave lens.
It's a standard lens.
Yeah.
So it's a uniform material.
Sure. Yeah.
I'm not really.
You bought this lens?
Yeah,
Or?
We bought the lens.
Yeah, it's a Rexolite lens. It's a high performance plastic.
Yeah.
It has a constant dielectric coefficient.
So currently we are transmit that mobile station and get a reflection over here. So basically we are picking up the long line of sight over here.
So how much gain does your lens have?
13 dB,
Yeah.
supposed to be 13 dB.
13?
Yeah, but it's actually
We measured it
smaller.
at 13, I think, and theoretically, I think we're supposed to get 30 or something.
So it's a great loss.
30?
Yeah.
That's 17 dB. That's a factor of almost 50. That is a factor of 50.
Yeah.
Really?
So there are some strange power loss over here.
Who designed the waveguides?
I think we bought this as well.
You bought the waveguides as well?
Did we?
Yeah, I think someone in our lab designed the manifold that the waveguides go into.
Okay. So what's the ERP do you have?
What?
What's the effective isotropic radiated power?
Wait, say that again?
How much power are you transmitting at each channel? Oh, this is the receiving.
Yeah, receiver. That's a transmitter.
So transmitter, you have two transmitters?
Yeah.
So it's a NIMO, two transmitter?
Well, the transmitter side is a single antenna structure. So
Single
it's-
antenna, right?
Yeah, there are two of them.
How much power was that?
The transmitted power is about 15 or 20 dBm output power.
What frequency was that?
28 gigahertz.
28. Okay.
Because basically transmitted power is relatively low, but surprisingly we can still decode it for a super large distance. So the longest
I
distance.
mean, 20 dBm. This distance should be no problem.
Yeah, this distance is good. So the furthest distance.
Yeah, your cell phone measures a minus 90 dBm.
So the furthest the distance we did before is about 20 feet.
200 feet.
200 feet. Sorry. Yeah.
200 feet.
Yeah, it's outside. That's the largest distance we got. And I'm pretty sure we can even go further because at 200 feet the constellation looks super good. So we can still go further.
What modulation you're doing?
OFDM and clamp.
All right. Who built the radio? Which company get the radio? Denai or?
You mean the antenna array? These?
No, the transmitter.
It's all constructed using off-the-shelf components. We
Oh,
just
so
strung
you
together
buy the
mostly.
components and you set it up.
Exactly. Just like on this end, we have.
So you wrote your own
Fantastic.
MATLAB or LabVIEW control?
Yeah, MATLAB and FPGA control. Basically, we use FPGA a lot in here.
Okay.
Yeah.
Okay. All right. Thanks.
Yes, curious, but actually this is this guy is listening.
Yeah, it's non-line of sight bouncing off of the wall.
So, okay. It's bouncing off the wall and then it's listening.
Yeah.
So what's the purpose, like what are you doing?
So it's demonstrating the lens architecture for beam forming. So we have 4-degree beam widths, and each bead corresponds to a beam, and the lens focuses the incoming signal to one of the array or one of the feeds based on which beam we're selecting. So we can select up to 4 beams simultaneously because we have 4 RF chains. And so we sleep through them all and see which beams are receiving the highest power, and then we select the 4 highest power beams, and we just receive on those ones, and then we're able to decode messages.
So basically you're imaging the thing that you're detecting here, right? That's what you're doing?
Yeah.
Are you imaging the information or the reflected data that you're receiving through the array? That's what you're doing?
Right.
Good. Thank you.
Yeah.
They're pretty much at the same beam, most of the time. And I don't think that's the only non-linear side we are receiving. I think there's something else. There's our waveguide is wide beam width stuff, which potentially causes a lot of reflection. Do you still remember the time when we pointed that way and receiver points straight forward and we still got the center point? I still think that's something maybe is wrong measurement. There's definitely something wrong with our code. It's hard to yeah, it's hard to. I mean, well, because you successfully blocked that somewhere when you move back, so it's I don't know what is happening. That's 6个 data block， 就是我们全部检查出来的。其实你看它的效果会啊，256。它一定会用到的病，这样会看出来。这是我这儿。You don't want to buy scope every month. So right, so it's getting hard to sell them. Because basically they don't sell a lot for each of their components, not each of their products, but they keep upgrading their products. So
they could sell like software.
Yeah, they do have software updates, but well, it's not a volume stuff, right? So you just there are just 1 or 2 order every month, or even every year, but because they are super expensive. So
like a subscription model.
Right. And also they become now the PSAT is trying to focusing more on the software part. Because they start talking to me about the computer vision and machine learning stuff. So it seems like they're gonna try to do some sort of, OCR, like optical so it's like when you handwrite some paper, right? So you scan it into the PC and you can read out the information. So they start doing some sort of equipment which can do this, which is or something like that, but it can get the information automatically. So, for example, you got a receipt, right? But it's a handwritten receipt. Some part is handwritten, some part is right. And you want to it's just like when we go to the hotel, travel for global companies. Yeah. So it's like, so currently you got the receipt, right? They require type in the information manually. So what they want is to scan it and everything. Yeah, that's kind of hard to do this. This time when I go back to home, I was working on this as well. So yeah, actually focusing on the Chinese character recognition is different from English characters, right? They already have a lot of libraries developed for that recognition, but not for the Chinese characters. You know,
there are a lot of like involved neural network stuff.
Yeah, but they will be super slow. So that's one thing. And another thing is the number. So regularly the number is just simple, right? 1, 2, 3, 0. But in China there's another way to write it. It's called discovery problem. That part is actually we are actually working on that, and there's no company working on this right now. So once we can make it work, probably a good chance to stay that one. So this is why I'm working on my I mean, I'm not really good at this image processing stuff, but the basic signal processing is really good. So this I'm basically focusing on some sort of pre-processing. Yeah, pre-processing methodologies, like for the image you grave it and you do the binary value of the image or something like this. And when you do the auto correlation or something like that, it helps you to calculate the upper line of so edge detection. Right, edge detection and the position, because most of the receipt is partially printed and partially handwritten. So as long as we know where the start position of the printed, where the start of the printed stuff, and we know where it should be what. Right? So we don't have to scan all the information. We just like locate it and find it and grab it out, and we only need to recognize part of the information that will be produced as speed. So it will be way faster than the convolution neural network. But still, it's really hard because I mean, ideally all the receipts when we scan it will be the same size, exactly the same size, right? But most of the time there will be slightly different between different receipts, which you have to like create a constraint for the size of the picture you're going to process, and also the quality of the scanned pictures is not so good.
And we can select 4 beams simultaneously with these auto switches, and we have 4 chains to support that. And then, processing in MATLAB, and this showing we can decode each of the mobile stations. So the data is actually being sent simultaneously. Yeah. And then this is showing which beams we select for each mobile station.
So it's kind of
Yeah. What's that? Yeah, constellations. Different rows are just different OFDM symbols in our frame. And yeah, so this column corresponds to mobile station 1.
Where does this point you to that direction?
Yes, it's receiving a reflection off the wall from the transmitters over there.
So maybe I should put a mirror there.
Well, it seems to be doing well enough.
That's good. So this is where that do the lens stuff, right? Where how you inject into it. You know, this getting this part right is not easy, right? There's angles.
Yeah, there's a specific focal distance
Yeah.
to use with this particular lens.
That's why you need that very accurate movement and calibration to get it right, right?
Exactly.
This is supposed to be the optical table things that you guys do this. You know, you would go to somewhere that people use an optical table with those big ones and then calculations, right? Yeah, robotic people usually have those things. It's really, really hard. How sensitive is this? You know, if this things, you know, is the future probably will be some housing mixed together, I guess, right?
Yeah, we haven't played too much with how changing the focal distance affects the constellations, but
yeah, you know, because otherwise you don't want a user to tune it.
yeah, but we can also move side to side, and then I'll get this a wider angle. So if we move it this way, then we can excite beams that are more that way. And
this is amazing. And these are directly connected to where's the power amplifiers?
we got
here.
LNAs here.
Okay.
Yeah.
So this is the receiver, right? So this is all the LNAs here.
Right. Yeah. So it just goes through RF switches, and then band pass
How did you convert from that waveguide stuff into electrical voltage signal? Now that's a waveguide, right?
Yeah. It has whatever these adapters on the back that go to SMK connectors.
Okay. So they will come sensing this EM wave and become some electrical currents get into here.
Yeah.
I was surprised. I thought they would use a sheet cable or something.
Is this something custom or you wrote it?
We had the manifold was specially made for us, I think, and then we just have the waveguide antennas inserted into it.
Manually.
I think so. I've never seen it apart, but yeah.
So the manifold was designed by some of you?
I think so. It was before I got to the lab.
This is a multi-year project. We got good work.
So what are you trying to show?
So we're sending from 2 mobile stations over there. Very non-line of sight communication, so it's bouncing off of walls and stuff over there. And then it goes through the lens, which does the beam forming. And
How do you know that it goes through the lens?
So I guess it's potentially not going through the lens, but the lens is supposed to form the beams for us and focus the incoming signals so that each beam corresponds to a single beam that we can select with a 4-degree beam width. And we can select 4 beams simultaneously because we have 4 RF chains, and we do that with RF switches.
So how essential is this configuration? What's its purpose? I don't understand.
So if we didn't have the lens, then we wouldn't be able to get narrow beams.
On the receive side or the transmit side?
On the receive side. And so here we're decoding the signals from each mobile station. The data is being sent simultaneously.
我这个2个发射机 FPGA 的设计差不太多，我是2月份拿到的版。
What are you using as a modulator and demodulator?
OFDM.
No, in terms of hardware. These RF signals are being sampled and processed.
Yeah, so we have 4 DSP makes the ADC and DAX card with the TI chip on it, and it goes to the Xilinx FPGA.
What demodulates it from the 28 gigahertz carrier wave?
What's that?
Where does it get demodulated from the 28 gigahertz carrier wave?
At the IQ mixer, takes it to the baseband.
How about the transmitter? Do you have to build the transmitter or are you using some custom?
Yeah, we built the transmitter similar to this. It's all off-the-shelf components, so we kind of strung together.
But it doesn't have a bump.
Right, it's a single antenna.
It's a single one.
Yeah.
This is the receiver station. The transmitters are over there. There's 2 of them.
Yeah. It's a reflective part.
Yes.
Yeah, so and these are like omnidirectional?
No, they're just waveguides.
Yeah, so if we just do temporal filtering, then you see that
if you get rid of this and maybe put a horn antenna over here,
Maybe put a what?
horn antenna, like why is this lens important?
This lens is there to focus an incoming beam onto specific locations on the array.
Oh, so it's not just one position. There is multiple focus points. Is it?
Yeah, where the beam is focused on this array depends on where the incoming signal is coming from over
So
there.
it would be selective,
Yes.
antenna selective. You select one of these.
Right now we can simultaneously select 4.
Okay. And those are being photo.
Yes.
What are those graphs?
These are decoded constellations. The left side column is from one of the mobile stations, the right side column is from the other. And this is, the yellow squares are the specific antennas that are actually being selected for each mobile station.
probably 5, correct?
Are these the switches?
And when did the program start?
These are the RF switches, right?
These are the RF switches.
These are RF switches, right?
Yeah, these are RF switches, so they are working for 28 gigahertz, and so we can switch to all 16 beams at here. Now we got 4 RF chains over here, which is independent with each other, and we decode them separately.
So, is this all at 28 gigahertz?
No, so here's a switch and goes to the bandpass filter. Now we get a low noise amplifier, and this is a mixer which is mixing down everything to the baseband. And here, these 4 boards are for the baseband amplifier, so they are voltage
so this is a
control.
receiver?
Yes, our transmitter is over there. Yeah.
So do you still have on the transmitter, you have an up converter and then
Yeah, we have the same architecture, but at the transmitter we are using single antennas, so it will be way simpler than this one.
I see. And here these are like a bunch of, you can basically multiplex the antennas.
Right. So now we are automatically select the 4 strongest beam, but if you want, you can select whatever 4 beams you want and fix that position. So you will have 4 fixed direction beams pointing to the specific area you want.
So, I mean, you're not transmitting anything to this, right?
No, this is just a single link for now, but we do have the circulator that we can do a double side trans and receive.
So what material is
this is dielectric, but basically it's just
Brixolite, it's a high performance plastic. Brixolite. And it's a high performance.
开1天了。
Good.
住哪儿啊？你来这？我自己找了个酒店，在外面找了一个，我没住这个会场这边。到这边，你们这儿挺贵的，不对，不谈这个酒店。
How much is that Red Hotel every night? Is that about 200?
Hotel Red is one of the more expensive hotels in town.
Oh, really?
You rarely get an opportunity to be in front of this.
It probably depends a lot on when you're staying.
Just like a state budget for the public.
Anyway.
Yeah. I think for Wisconsin it should be 100 state budget. Okay. But it's a little bit higher.
This is a single carrier, right?
So you can kind of visualize pilots know that we have the different pilots where their slots and you can data packets and there's a little blip in the middle.
So those are WR12. WR12? So that's 60 gigahertz or is it 70? 70 gigahertz, okay. I thought you didn't have it. You only have a 20.
Island frequency signal.
Oh, 71 to 76. Oh, okay.
And then this is what? 64?
Well, the connect base on the same.
Yeah, well, it's like, if it's a WR12, you can just toss it out. You can,
Still really good. We got this frequency.
Okay.
I see.
So we have our-
Try it.
Yep. Well, that's it. If I find it, I think something will happen.
Oh yeah, let's see. Yeah, this is that's a good point. But we need a thinner feed.
This is a WR10.
What aspects of this?
Is this 73?
77.
Yeah, it's a
So we
WR12.
can connect it there.
So it's not. It
What frequency are you familiar
This is a WR10. 75 to 110.
Oh, so it's a little higher.
Yeah. But we have other work. Fuck it out.
So what would you see? Alright. So I want to talk to you tomorrow. Okay. Maybe at dinner too or some beer. Okay, so that's cool. This is your 2 gigahertz now? 3 gigahertz. And then what's your sampling rate? 2, 4?
A little over 3 gigs a second.
Okay.
It's a multiple of the LT. 70 gigahertz.
Okay. And this is the, what is it? Is it input?
This is, yeah.
What the hell is that blip?
We're
Is it like
really
a-
close.
Oh, so there's reflections?
There's some reflections, there's some side lobes, there's all kinds of
So
stuff.
wait, so this is 73, right? So would it reflect from, let's see what,
Go for it. Yeah, play with it. Play.
let's point. Dave, you point that and I point that. This is a mirror at 28.
I also don't have the power cranked too high.
Yeah.
We can turn it up if you really want to get crazy.
You know, I should be careful because I have broken one of your
Our
demos.
20 version is going to take
So just keep it off,
Yeah.
push it back. This is the fan, it pushes hot air.
Sorry.
Oh, you're good. These are fine, it's the radio system.
Yeah, there is a little multi-track, and it's probably a reflection. Okay. Very cool. And so what can we play with? Say if you wanted to. So this is your API. So that's the frequency response of the channel. Okay.
So one thing that we can play with so if you want different frames right now.
我清华麻省理工前面都不需要。
那倒不是。
是的需要。看人吧，可能看方向，有些方向确实不需要。你不要觉得麻省理工真的很强，它很多方向需要。
So at what rate is this being updated?
I'm not sure because this is all being done on the coast, so it's non-deterministic. So this is showing the constellation as it's been processed in the FPGA, and we're able to calculate the So for example, I can turn off my FPGAs. So that's the activity support, and it's all in when you degrade at a certain point, this is showing what's actually running.
Very cool.
Honestly, we don't have it set up to change a lot of things in the physical layer. We've been using this for more recently is doing beam steering. So we have a phased array that we have, and we play with the beam.
That's what you're having in the Inoki way?
For this one, we're using a SiBeam RFIC.
Okay.
For the Inoki Wave one, we have a completely different API, and we're running that OFDM based.
Very cool. So, okay, so now...
we have not incorporated all of this.
So, there's a whole bunch of things going on there, like you have your frame, and then you have your stuff, and if you wanted to, so you not do too much here, but you wanted to that's new. Yeah. No, but but you could have it in the API, right?
Oh yeah,
Say
if you wanted to add
power,
something. It really depends because we split where the processing's done. If it's something that we process on the host, then you can change it pretty easily. If it's something that's going to take an FPGA recompile, then obviously we'll do it.
Basically, there'll be 4 of these for the basic. Yeah, and we could.
And your UE, honestly,
we can put it this way too, or should we?
Your base, the UE, all you would add on would be the FPGA, and the rest of it would look exactly.
I mean, they're based in Santa Clara.
One other thing to mention. So if you look at the quote for the radio heads, the 71 to 76 gigs, we have a transmit head and we have a receive head. For the other frequencies, we have a mid. So that's why you'll see that quantity.
I see.
So anyway, just something to keep in mind. The quantities are right.
Yeah, so we are incorporating. Started with
Okay, cool. So yeah, that is. So is this this API is part of LabVIEW?
Made in London. You can actually see This is what a LabVIEW project looks like, and so we have it broken up where some of these are, so the ones with the little notch right here, those are FPGA pieces. So we have a bunch of stuff that's done on the host, and then and then these are actually specific modules.
So, okay, I see. So if we wanted to, so if I say we're going to put a different modularity, we've got to join those, and they are dedicated FPGA for each.
Yeah, I see. Well, actually, I'm not really dedicated to FPGAs. We say, okay, we want the decoder to run. Yeah. Honestly, LabVIEW handles that for you. Okay. You don't have to split between one FPGA or the other. You know how many resources you have to run, and that's what you get to do.
Yeah. But what if the hardware breaks? Then what are the diagnostics? Then I want to know where's what.
Well, I mean, if a single part is broken, that part will throw there. If hardware is broken, nothing is going to happen.
All right, very cool.
Yeah.
Thank you.
Let me know as you think of questions.
Yes, thank you. Yeah, I will, definitely. And yeah, I think at 5:30 we can talk about we have time. Hi.
So you provide different bit streams for like different functionality that, or is it just behind the
What do you mean by bit streams?
Precompiled FPGA code.
So I mean, I have my entire project, which is my source code, and then I compiled that project down. Determines how that compilation is split between my FPGAs. I don't necessarily go in and decide. Like, there's some stuff that specifically you were this FPGA, and we have different ones. We have Kintex and Perception here, so there's some split between it. But for the most part, you're spending time thinking about like what's one FPGA to another. We have it's called peer-to-peer, stream from one peer to the other, back and forth, and that allows sharing of data between FPGAs very, very easily. Like you just drop down one little icon and it takes care of everything.
What's the backlink connection?
So PCI Express. PCI
Express. Mm-hmm. So you have a root port in the PCI, and like the wait, this is point to.
Yeah, we have some proprietary technology in there too for how we do our data streaming.
Okay.
But I mean, the goal is to make FPGA programming more accessible to people who aren't HDL experts.
Yeah. Okay.
And even people who are HDL experts, it's still a really good tool because you can get as low level as you want to, but at the same time, it handles a lot of I/O abstraction. So
it's a pain, and you're not doing your actual research while you're doing your I/O.
Exactly, and it's just something that's kind of not necessary.
Yeah.
For you to be concentrating on.
So this system gives you like the data path from your receiver to the computer, and what you do with the data, that's up to you, right?
Yeah, and that's all done, and that's what the software that we're running is doing. Yeah.
Okay, and are there ways to like? There's got to be ways to change what kind of processing you do on YouTube. Okay.
Oh, it's open. It's all source code. It's just, I have bit files I've already compiled, so I'm running them.
Yep.
If you wanted to change them, you go and you make changes. Some stuff runs on the stuff runs on the PC, so you may or may not have to recompile.
And say you want like a certain functionality to run on the FPGA because for some whatever reason your PC's not handling it as well as you can do that.
Yep.
All right. Thank you.
publications that post
哎
on that
好
site.
好问题，为什么不做人 PCB 脚本？万一年轻人就在我这生气。要有人会，我也没意见。28G 怎么不行？
这块
这块做完
没法，
这块做完我天天都拿到，我还
不这块很精良，需要很大的经验。你说这个 PCB 板，我不知道。
罗杰斯买最贵的罗杰斯，就结束了。
就你要那块就 PCB 板那块钱。The antennas is that everyone does that?
有个东西叫蛇形无线。
So the lens kind of makes this prototype different from other prototypes where you might do like a phased array for so the lens kind of replaces the need for a phased array in order to do beam forming. So we can form really narrow beams with by just exciting single antennas. It focuses the
So if you excite one antenna, it goes one way, and you excite another antenna, it goes the other way.
Exactly, yeah. Yeah, so actually in this setup, this is the receiver and we have transmitters over there, so depending on where the transmitters are located, we receive on one beam or the other beam.
还不多啊，5万啊！你想多少？画个板。
We have 16 antennas, but we can only measure from 4 simultaneously because we have only 4 RF channels. So the lens really cuts down on the hardware complexity.
而且不要
We just use switches to switch between them.
These things are just.
而且很多是没有道
The
理。
switches are actually right behind the antenna array.
Like the peregrine switch or something. It's an SLI switch.
Say that again?
Just some off-the-shelf demo board, switch demo board.
Yeah. Pretty much everything here is made from off-the-shelf
说这个
components.
频率我们这样走一走，然后你一看，我说我操，这样一走是一条线全部出去。
You guys actually write? Are you guys more into
然后
more
我们先做个电磁
RF
一个什么
people, or are you ones writing the DSP code in there to do the signal processing once you got it down into the digital domain?
Yeah,
both.
we do. Well, we do a little bit of both, but we do a lot of the DSP and stuff and FPGA work and.
Most of the signal processing most of the signal processing uses MATLAB Toolbox, which compiles MATLAB scripts down to HDL. But some of the data backbone is custom VHDL.
So is Professor Said, is it mainly communications theory and the hardware is just sort of you needed to do your research, or does he actually get involved in a lot of the hardware? I mean, you know, switches and stuff, that's easy, but does he get involved in the EM part of it as well?
We haven't done so much of that. After we figure out which components will work for our system and get them working, it's pretty much all figuring out the DSP.
And when he says, I want a test bed, is it basically he wants something like this as a turnkey solution?
Yeah, so after we get this really robust and working well, we're going to make a bunch of these, or a handful of these, and more mobile stations, and we're going to take it out to the field out there and set them up in some configuration and create a whole network.
So will you do the entire protocol stack of that network, or will you borrow it from LTE, or
We're probably not going to get to the point where we do the protocol stack for a long time, because initially it'll be mostly for measurements, and also as a proof of concept for lens-based beamforming on beam space array select.
So basically the lens.
No, this is a switch. So we have
is a physical implementation of what you guys consider beam space, the mathematical definition of beam space. That's the physical representation.
Yeah.
It does the physical transformation of the mathematical that you guys
Exactly.
So we have 4 RF trays over here, and it goes to the band pass filter.
And can you do that? Can you make the antennas? Can you cover the entire hemisphere? And,
Yes.
you know, to get.
But don't you need
How far have you tested?
More,
Like 60
more
degrees?
coverage, or is that just a lens design problem?
So yeah, we could have another feed array sitting right next to it, and we'd be able to excite more beams. And actually, we've done a few tests where we tilt the lens back and forth, so it's way less.
This is connected to. I don't
The
need
gain
that.
does fall off when you get to really
Just
steep
between one out of
angles,
these.
but
Who did the
So it's like you only
lens
want to
design?
activate one RF channel?
Student here?
Well, then you can just
I don't know if we
Pretty sure we
designed
bought that
the
one.
lens ourselves, but we
we
bought it.
power single power.
We bought it from a
I want to
company
be the most powerful feed, and you just enable that.
What are these antennas?
Way different than when I was in grad school.
No, we didn't make just all them. Yeah. So basically, all the RF. I think we got the whole thing, right? Chris, did we bought the whole thing over here? The whole antenna feed, right?
I think I don't know.
So basically, all the RF.
How many students are working on this?
Maybe 4 or 5, but it's been going on for like 3 or 4 years also. So a lot of this was, I've been here for years, so still learning a lot.
And then you can move the side, and you can see the activated gain block move to the side as well. So if you want to recenter the whole thing, you can just move it to the side. So it's like a being tracker. Half of wavelength.
How do you, on the receiver side, how do you distinguish, how do you remodulate these for screens?
Oh, you mean?
So we have,
Is that like just conventional MIMO techniques, or do you have
No, I think the
Curvature is the same as this curvature?
yes, and the distance is 6 feet, 6 inches. Yeah.
What happens if there's an error between this curvature and this?
Is there an error?
Like I suppose you match this curvature.
Yeah.
This curvature.
You will get the most powerful gain, but if they are not matching, there will be some like mismatch problem.
Wait.
So
Isn't this just put at the focal point?
yeah, this is put at the focal point.
So
I mean, they
That's
should
the same as this, right?
right because the focal point is actually a focal surface.
yeah.
So I mean, ideally, if we put the receiver at the focal surface, you will get the most significant power. But if that's not, I mean, if you are not matching them pretty good, like there's some sort of off. So just imagine you got a, so if there's an optical light coming, it will not focus at the correct point. So your power will be smaller than you expected. So actually, this is something we are suffering now because the gain of this lens should be 30 dB, but what we got is about 13 dB. From this lens. So there are some sort of mismatch existing.
I saw this once before. I haven't seen this particular demo.
Okay. Because this is a multi-user non-line of sight demo. We didn't do this before.
maybe on one beam.
So this is QPSK?
QPS. Yeah, QAM.
4-QAM.
4QAM, yes. 4QAM OFDM. Yeah.
So those are the 5 subcarriers. You have 5 subcarriers?
No, these are actually the data blocks. So we have several data blocks. We have 256 subcarriers. Yeah. So basically, we decode all the data blocks and show the constellations. So actually, you can see the constellation result is actually varying even between the data blocks. So the channel is actually.
Where are you doing the computation?
It's in the MATLAB. So we are working on the online processing. So put the whole processing to the FPGA something.
Okay. So
now
you're buffering data and then.
No, we are. Actually, we are buffering the data, but we keep feeding the data into the PC, and PC just process and display it and refresh it. And the data goes through the Ethernet over there.
What is the bandwidth? The channel bandwidth?
It's a 367 megahertz. Yeah. but it can.
I know you were talking about wider beam squinting and all that, right? So have you tried, say, 20% channel bandwidth?
Yeah, and actually also we can go up to 1 gigahertz, I guess, because the bandpass filter here we designed is for 1 gigahertz bandwidth. So, if we got a really faster DAC and ADC, we can go even a higher bandwidth.
Cool, thank you.
Thank you.
那你这信道估计完了一直使，你这信道估计完了使多长时间？
信道估计完了以后什么？
估计了信道，
估计
估计完了使多久？
估计完了是多久？什么意思？
就用多长时间？
哦，每一个 frame 单独做。就我们就是16000个 sample 做一次。
frame 是256个心头还是？
不，我们一个 frame 里面是这样，一个 frame 就里面有frame sync 这些东西，对吧？然后我们不停的在重发这个东西，就是你就理解成每16000个 sample 做一个 channel estimation， 差不多这个意思。
那这段时间信道已经这样。
没办法，所以说这个才会变了，就会变。
不是，你说你之所以有时候变得特别差，比如像这样，很有可能就是跟信道
估计完了以后信道就变了嘛，对啊，
就信道就不对。
是这样的，是这样的。
那你不能加点什么自适应的？
我又不管，你跟后面人说，跟你后面。This price.
Yeah, hasn't crashed yet today.
Yep.
Photographs and microphones.
I don't think I'm gonna come, so.
Start 8:30. I will be here. Yeah, because we don't have to set up the prototype or anything tomorrow.
So you do beam selection based on RSSI, right?
Based on what?
RSSI.
What does that stand for?
Receive signal strength.
Yeah, we measure it at a specific part of the frame, and we just do, we measure the power on each beam and select the...
Wait, so how much pre-processing do you do on each frame before you select which beam you want to do the rest of the processing on?
So there's a frame sync stage where we pretty much figure out where the start of the frame is, and that way we can index to the other parts of the frame based on that. So we kind of need that part to know where the part is that we want to take the signal power over.
What does the frame sync involve?
It's a random BPSK signal.
Well, actually, a non-random BPSK, so something like that.
It's a known random BPSK signal that we do a correlation with.
What's a BPSK?
Binary key shifting. So it's basically 1 minus 1, 1 minus 1.
Yeah.
So it's just a magic number. Basically.
Well, it's a random sequence that it's transmitted, and then we know the sequence here, and we correlate with the entire frame.
No, actually, that's
what the highest
randomly generated
is.
sequence, and
right. So it's a magic number.
Yeah, or no, actually, because if you correlate it with itself, you know what the maximum number it is, right? So when we receive the data, we do the same thing and calculate that number to see if it's higher than the specific data. It's higher than we think it.
Wait. So how do you? How would you do this when you're like doing a live data transfer?
Well, once you frame sync it, it doesn't matter, right? Because everything comes...
But you have to catch the start of the frame in the first place to be able to decode the rest of the message.
Right, so this is why we got the frame sync, right? As long as the frame sync is correct, then you know where...
But then you're still scanning while you're...
Well, every scan, I mean, every capture will make sure that you contain the whole part of the frame, like the frame sync, data block, everything. So there's some sort of cheaty stuff.
So there's like, when you scan, you do a long enough sample on each channel.
Right.
Doesn't that bottleneck your scan?
Yes.
Okay.
Yeah, so we can only read 4 feeds simultaneously, so we have to read one and then switch and read another and switch.
This is why this is still not the...
So you have to take a long time to lock onto a beam before you can do like a burst transfer.
Yeah. And there's still a lot of work to do, especially at the FPGA side. Because I mean, if we can implement the processing in the FPGA, then we will be able to do whatever we want. Because you can just do the protocol inside the FPGA, which keeps streaming the data into that protocol, and basically
that's the only way it's going to get faster.
Yeah, I mean, and you don't have to worry about whether I capture long enough frame or not, because as long as you are keep feeding the frame, it will sync by itself and decode correctly.
So right now your frames are zeroed out when there's no active transmission. Couldn't you do a level trigger?
What do you mean?
Like on an oscilloscope.
What do you mean?
Like a voltage level trigger.
So we just start recording when it jumps past a certain voltage?
Yeah.
Yeah, but we don't necessarily know the signal strength and we're changing the distance also. Okay, so
but
it might be
but
really
background noise has to be much smaller than...
Actually, it's not.
It's not?
If you are really far distance, the background noise will be basically as large as your signal power, most of the time.
Then how can you get good constellations out of that?
Because for the frame sync part, right? For the frame sync part, we use a 4 scale because it's 1 and -1, which we basically use a 4 scale. So most part of the frame is almost the same as the background noise, but there are some peaks happening. So you correlate it. The correlation will still work sometimes, but not always.
Yeah, so to get good constellations, it has to be a little bit above the noise floor.
Right, because if you scale that up, you scale up the noise too.
Right.
So that brings me back to the level trigger.
Yeah, so we could start collecting data based on a trigger, but then how would we do the beam selection? We still have to measure signal power on each beam anyways.
That could be a really simple indicator on board of which beams you shouldn't bother looking at. Right?
Yeah. Okay. That could work. But even to do a level trigger, you have to switch to that feed, right?
Oh, right, because they're not hooked into the FPGA at the same time.
So I guess you could have like some physical hardware thing that's...
Like a level trigger on the line.
Yeah. That'd be interesting.
It's almost the time. Do we need to shut down? Just wait for 2 minutes, I guess? Sure.
Could you use a shorter sync sequence?
I mean,
so you can take shorter samples, sync up, and then use
we test that.
Lengths.
Or like
but the result is almost the same. But I mean, technically, longer
why is it almost the same?
Yeah, that's something. Because ideally, a longer frame sync will give you a
I can't imagine a 16K frame is necessary.
So
for
our
syncing.
actual frame sync block is only 130 samples.
Oh, okay. So you don't need the 16K. You're just doing that to capture the entire
16K
data
is
block.
for everything, including frame sync and channel estimation and transmitting the data.
So we take a full capture of the data we want.
So like eventually it would be way better if you scan for the frame sync symbol
Yeah.
and then do a handshake
Yeah.
and then do the long capture.
Actually, this is what we need to do with a circulator, because a handshake you need to transmit from the receiver. You need to let the transmitter know that we are synced.
And that there's some Mac protocol shenanigans with that.
I mean, this is basically the protocol for all kinds of communication, basically. I mean, even for wired, like I2C, SPI, all kinds of these.
Well, those are shared bus protocols that use like a medium that doesn't really get a lot of use.
But I mean, for most of the communication protocol, you need a handshake.
Well, OTA is very different from wire.
Okay.
What is RTA?
Over the air.
Oh,
Like, especially if you're not listening all the time, right? Because most of the shared wire bus protocols like I2C, every device is listening 100% of the time instead of 50% of the time. If they were listening 50%, if they were listening 50% of the time, then the bus wouldn't be very efficient.
Yeah.
And that's what you're doing. You're listening 50% of the time.
Right. Yeah. I mean, I think the idea is that you're only listening for 50% of the time, but you do the beam selection once, and then assuming nothing moves, you can use that and select the beams that matter and listen 100% of the time.
Yep.